This is problem 80, and they'll give us a reaction. It looks like a decomposition of methane. And so just right away you might want to think maybe what's happening to delta S. So it looks like entropy is increasing. Not too sure about if it's endothermic or exothermic just by looking at it. It's decomposition, so it's possible that it's endothermic. But this question is not really asking about those types of things. It's saying to use data from Appendix C to calculate delta G standard. So you can find delta G standard two ways. You can find delta G standard by using delta G standard equals delta H standard minus temperature times delta S standard. And then you individually do products minus reactants for the delta H and products minus reactants for the delta S, and then plug it into this equation. But also in Appendix 6 we have delta G standards. And again, on a test it'd be depending on what's given to you because you wouldn't have the table to reference. So because we have delta G standards, we could do products minus reactants for just delta G standard. So the delta G standard would equal the delta G value for C3H8 and 2 hydrogens minus 3 CH4s. And just make sure that you use the right state of matter. For CH3 we have negative 23.47. For hydrogen, we know that for delta G and delta H, because hydrogen is a pure element substance in its natural state, it's 0, which we can't do for entropy. And then minus 3 CH4s, which is negative 50.8. And so doing this works out to delta G standard being positive 128.9 kilojoules. So that answers A. And then B asks us to find delta G without the standard condition. So delta G equals delta G standard plus RT natural log Q. And so we just found out the delta G standard to be 128.9 kilojoules, plus R is going to be 8.31. Some worksheets we're using was 8.3145, and the textbook uses 8.314. On the AP equation sheet, it just has 8.31. So whichever one is fine. But we do have to remember that's in joules per mole times Kelvin. And so because we're using in the delta G equation, we have to divide that by 1,000 to have kilojoules. And then our temperature is 298 Kelvin. And then we're going to do times natural log of Q. So remember, Q is products over reactants. It's related to equilibrium. And we have all gases here, so we're going to include all of them. So it's whatever C3H8 is, which they're telling us is, and so I'll make this equation here in the Q value. So 0.01 atmospheres for C3H8, and there's no coefficient there, so we don't have to worry about it, times hydrogen's partial pressure, which is 0.018, but don't remember we have to square that because we're doing equilibrium, so we have to put a 2 in front of it, over reactants, and again there's a 3 in front of CH4, so we have to do what's given to us for 40, lots of reactants, which we have to cube. And so if we plug all that work in, the delta G will simplify to 70.2 kilojoules. And again, we see that it's positive, which we kind of could predict very easily because we have in the problem they're telling us we have a lot of the reactant, right? So that means if it's in an equilibrium, it's more reverse. So we'd imagine that delta G, going in the forward direction is not happening spontaneously. So it would give us a positive delta G value.